Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. First of all, sorry for the long time that has passed since the last video. First, my camera broke and I had to buy a new one. That's also why you may see more shadows than usually, because I'm still trying to get the perfect settings for everything to work out. Also, after that, I had to focus on my university access exams. Then I went on vacation, so a lot of things added up, and I couldn't record up until today. Hopefully, I think I will be able to finish the summer at least till I start my new semester, having one video recorded per week and posting it in the channel. Furthermore, I have to announce that we're going to start making some shorts for the channel, and they are also going to be published in a new TikTok account that is going to be created for Physicawesome. So in today's video, we will start with a series of 4 videos about collisions. First of all, we're going to talk about the different types of collisions that we can find: elastic, inelastic, and superelastic. And after that, we're going to start with the 2 cases. We are going to treat elastic and inelastic collisions, finding some equations that will be useful and different things about them. So let's start. Right, let's start talking about collisions. A collision in physics is a situation in which two objects face each other in different directions and then they collide, and after that they go on each way or they remain together, move with each other. So there's different situations, but we have to look at 2 quantities that we have seen previously. First of all, momentum and kinetic energy. Those are the 2 quantities of interest for us. We're going to have 3 types of collisions. First of all, elastic, as we said earlier, elastic, inelastic, and superelastic. In every collision we have, there's one thing that is always going to be conserved. That is momentum. So conserved, conserved, and conserved. The variation of momentum, delta P, is equal to 0. However, on the other cases, with kinetic energy, it's not always that way. On elastic collisions, we say that the change in kinetic energy equals 0. So it's a convention. The collisions in which the change of kinetic energy is 0 are called elastic collisions. Then we have sometimes, for example, when a ball falls to the ground, in which there's also friction, there's sound, there's also some deformation that the ball may suffer. So there's energy loss. There's some kinetic energy that is transformed into heat, into sound. So we have a change in kinetic energy less than 0. And there's some other times, for example, when you have a bomb, in which if you throw it and you cross it with something, the kinetic energy is going to grow pretty high, because there is some external thing that has happened, for example, a chemical reaction in an explosion or similar, that has transformed into kinetic energy. And therefore we have these superelastic cases in which the change in kinetic energy is bigger than 0. Knowing these facts, we can use this conservation laws or not to our advantage, so that we can completely understand what is going to happen after a collision. Great, now let's focus on elastic collisions. We know that momentum and kinetic energy is going to be conserved. So we know a couple things about our system. Delta P equals 0 and delta K equals 0. We will imagine that we have two balls on a frictionless surface. So ball number 1 and ball number 2 that are moving towards each other with velocities v1, m1, m2, v2. And this is going to be at our initial state. After that, we're going to have a second state, which we're going to have m1, m2, and they are going to be pointing and moving to the other side because they have collided and now they are going each in its way. All right, now we can apply these principles to have that our initial momentum is going to be m1 b1 plus m2 b2. We will assume that our b2 in this case is going to be negative because it's pointing to the left and our I hat vector is still right and it's included inside of that. And then we're going to have our momentum at the end that is going to be equal because there's no change in momentum. So we have m1 b1 prime plus m2 b2 prime. In this case, it's a b1 prime, the one that is going to be negative. Now, we also have kinetic energy conservation. Therefore, we will write that equation 2 that is going to be 1/2 m1 b1 squared plus 1/2 m2 b2 squared, and that's going to be equal to 1/2 m1 b1 prime squared plus 1/2 m2 b2 prime squared. We could take all the 1/2 from here, and now we are going to have a set of two equations that are solvable in every single case. Because if you realize, if we know perfectly our initial state, m1 b1, m2 b2, we are only left with two unknowns, b1 and b2 prime. Now let's explore the inelastic case. Alright, now let's start with inelastic collisions. In general, inelastic collisions are pretty difficult to analyze. However, we're going to talk about a specific case, totally inelastic collisions, that happens when both of our objects are moving and in the end they crash together and start moving simultaneously with a velocity. Furthermore, we're going to make another simplification, and that is that we're going to take as our reference frame the second object, so that b2 equals 0. Now let's apply our conservation of momentum principle. As we are in this reference frame, b2 is going to be equal to 0 and our initial momentum is going to be m1 b1. Our final momentum is going to be equal to the sum of the masses times the final velocity. Now, kinetic energy is going to be a bit trickier, but we can still find some things that will help us when doing our analysis. Our change in kinetic energy is going to be our final kinetic energy minus our initial kinetic energy, and we know both of these things. We can express them in our different variables. So we have our expression for the final kinetic energy with both of the masses and the final velocity, and our initial kinetic energy of the first object as it's the only one that is moving. Now, we can take advantage of our momentum relationship to substitute it in here and simplify different things. We know that final velocity equals m1 over the sum of the masses times our initial velocity of object 1. Therefore, we can substitute this in here and find that lots of it simplifies. We can also take the common product out of this and see. And we find a combination of the masses times the initial kinetic energy is equal to our change in kinetic energy. Therefore, we can rewrite that and we find that this change in kinetic energy on our perfectly inelastic collisions related to the actual kinetic energy that the system has in general is going to be equal to a ratio of the masses. And we see that whenever our first mass is so much greater than the second mass, there's not going to be a lot of kinetic energy loss. However, if our second mass is huge, is very big, the loss is going to be pretty significant. Indeed, it can become exactly the kinetic energy. And that fits with our experience. Because, for example, if you try to cross a car against a wall, the thing that is going to happen in 99% of occasions is that the wall is much more heavier than the car, and therefore there is going to be a loss of almost all kinetic energy, if not all, that the car had initially. And that is what we see here, that it depends on the object that is standing still, in our case, and this ratio of masses. That is all for today. I hope you got a sense of the different things that collision. That is all for today. I hope you got a sense about the different types of collisions that you can find, and also how taking specific cases can help us find different equations that give us some insight about the situations we are analyzing. In future videos, we will treat 2D collisions and also some different reference frames that will be very useful when analyzing collisions. Any doubts left, you may ask them on the comment section. Remember to like the video if it was the case, subscribe to the channel, press the bell, and follow us on social media so that you don't miss any of our new videos. See you another day with more Physicawesome!